Let's talk about electric charge, which is more commonly referred to as just charge. All particles have this property, and they can be positively charged or negatively charged. This is referred to as polarity. Or they can be neutral, which is to say they have zero charge. And as I just said, charge is a fundamental property of particles. So what does that mean? Well, let's think about computer games, specifically sports games. In those games, the players have attributes such as strength or speed or endurance. And they'll have a value, say, between 0 and 100. So perhaps the strength is 90, the speed is 70, the endurance is 65. These attributes and their values dictate how that player will interact with everything else in the game. It's the same for particles. Particles have fundamental properties, of which charge is one. And these properties dictate how that particle is going to interact with the rest of the universe. In this case, charge dictates how the particle will interact both electrically and magnetically with other particles. So that's what we mean by saying it's a fundamental property. And charge is measured in coulombs. That is, this is the MKS unit for charge, the coulomb, represented with a capital C. Turns out 1 coulomb of charge is a lot of charge, and so it's not uncommon to talk about the charge in smaller values. So, for example, might be talking about millicoulombs. Remember, milli is 10 to the minus 3. Or we might talk about microcoulombs. Remember, that's 10 to the minus 6th. Another possibility, nanocoulombs, and that's 10 to the minus 9. In our formulas, charge is represented with a lowercase q. And this includes polarity. So as an example, I might be talking about the charge on object 1, and it might be negative 20 coulombs. So that's an example of how we use q to represent charge. But we also often talk about the magnitude of charge, which we use a capital Q for. And the capital Q is just the absolute value of the lowercase q. Now let's talk about protons and electrons. As I said, all particles have this property, charge. For neutrons, they're neutral, as are neutrinos, they're neutral. Photons are neutral. Electrons have a negative polarity. Protons have a positive polarity. And it turns out, and you may already know this, that the magnitude of charge on the proton is the same as the magnitude of charge on the electron. This is a very important fact. Since the electron has a negative polarity, the proton has a positive polarity, that means it's possible to have atoms or molecules that are neutral, that are perfectly neutral, because these can cancel out. Of course, not all atoms and molecules are neutral. Some of them are positively charged or negatively charged, but it's possible to have neutral atoms and molecules because of this fact. If we write this in terms of lowercase q, then we would say that charge on the proton is negative the charge on the electron. And it's important to note that for particles, their charge is fixed. It can't change. All electrons have the same charge, all protons have the same charge, and that will always be the case. We've never seen any violation of that. Now, I'm not talking about atoms and molecules. I'm not counting those as particles. I'm talking about the fundamental, I'm talking about subatomic particles is what I'm talking about here. Okay, the other big thing we need to talk about is conservation of charge. Physics has many conservation laws. There's conservation of energy, conservation of momentum, conservation of angular momentum. And what it means to be conserved is that the total amount in the closed system never changes. So if we're talking about momentum, I could have a bunch of electrons. Each of those could have their own momentum. I could have them colliding and mixing with each other. And as they collide, their momentums may change. Individual objects can change their momentum, but the total for the whole system can't change. If I add them all together at any moment in time, it will always be the same value. The total amount must remain constant. And it's the same here with charge. We're talking about the total amount of charge in our closed system. It can't change. It doesn't matter what's happening. We could have particle annihilation. We could have particle creation. Fusion's going on, fission's going on, all sorts of crazy things. It doesn't matter what scenario you can imagine. Charge must be conserved. The total amount has to remain constant. So let's take a look at an example. Object A has a charge of 100 coulombs and object B has a charge of negative 80 coulombs. Later, object A has a charge of negative 200 coulombs. What is object B's charge? Okay, so at the beginning, so at the start, I have object A, so its charge, and we'll assume this is a closed system. So if I add those together, so you get the total amount. So object A has 100 coulombs, B has negative 80. That, of course, is 20 coulombs, and that is the total charge. Now at the end, same thing. At the end, I know what A's charge is. That's negative 200. I don't know B's, but I know the total charge, 20 coulombs. And so I can solve for B and get 220 coulombs. So there is the answer, 220 coulombs. Now, one thing I want to quickly point out here, I earlier said that particles can't change their charge, but objects can. So what's going on here? It could be that I've got a balloon. Maybe I've got a couple balloons and I'm rubbing them together. Or rubbing one on my shirt or something like that. And so what's happening is electrons are being exchanged, and so the charge on the objects is changing as a result. That's how you can have a situation like this where the amount of charge on an object changes because you're exchanging, usually it's electrons that are being exchanged.